sort of as there's the standard lore that black holes break global symmetries, and so you can use black holes to destroy global symmetries, and I'm going to talk about how to basically change that around and use black holes to generate global symmetries. So the general outline of the talk is going to be, first I'll give sort of a motivation and sort of the general idea of how can you make black holes decay asymmetrically. And then I'll sort of talk about specific ingredients / assumptions that I made when talking about the general idea. And finally, I'll talk about sort of an application of this, which is the evaporation of black holes in the early universe. And finally, I'll tell you about some slightly related but a little different work that I'm doing with Raffaele D'Angelo at the IS. And then finally, okay. So the motivation for this is basically going to be baryogenesis. We see a universe that's full of baryons and not antibaryons. And so this is something we have to explain, because basically after inflation, we end up in a universe that has baryon number equals 0. And so right now, since we observe B not equal to 0, we have to explain this somehow or another. And so what has basically guided people in the past several decades, as people have thought about baryogenesis, has been Sakharov's 3 conditions. The first is you need C and CP violation. The reason for this is basically you need some way to distinguish particles versus antiparticles. If you want to produce more of one, you have to somehow know the difference between them. The second one has been baryon number violation, and that's simply the statement that I mentioned earlier, where after inflation we have B equals 0, and so we have to somehow explain how we got into the current situation where baryon number is not 0. And then finally, the state Sakharov needed you to be out of thermal equilibrium, basically because thermal equilibrium is a rather boring state, and nothing happens dynamically. So what people have done in the past to try to do baryogenesis is, so in some sense, the most compelling attempt is electroweak baryogenesis, because for that, the hope was that you didn't need new physics. And so what that did was basically, if you assume that the electroweak phase transition is very strong, then strongly first order, so then you have regions of space which are have spherons converting baryons into lepton numbers. And so you basically use the spatial gradients to generate a net B plus L. Unfortunately, this doesn't quite work in the standard model, basically because since we measured the Higgs mass to be 125, we've discovered that it's actually not a first order phase transition right now, but a second order. And so it doesn't work without new physics. The second popular approach has been just standard freeze out and decay. The way that works is that you have some gut particle. It has C and CP violating interactions. And then it has explicit breaking of baryon number. And so after these particles freeze out, when they decay, they produce more baryons than antibaryons. Some slightly less popular mechanisms that people have talked about are direct Theogenesis. The idea here is to say that, well, we're not going to generate a net B minus L, but what we're going to do is we're going to hide the baryon or lepton number in a different sector. So in the original approaches, they basically hid it inside right-handed neutrinos. You just had a Dirac mass, and right-handed neutrinos are actually not in thermal equilibrium with the rest of the standard model. And so you could hide it there, or you could couple dark matter to the standard model in such a way that the dark matter is charged under baryon or lepton number, and hide it inside, or the unobserved baryon number inside dark matter. Another approach is sort of the Affleck-Dine baryogenesis, which is the idea of using coherent scalar fields to do baryogenesis. And then finally, I'm going to talk a bit more about the least well-known of these, which is spontaneous baryogenesis. And so what spontaneous baryogenesis does is it basically breaks this last assumption of Sakharov's condition, which is that thermal equilibrium is boring, or nothing happens in thermal equilibrium. So the idea behind spontaneous baryogenesis is simply, what if in thermal equilibrium there is B minus L charge? So this only happens if particles and antiparticles have different energy levels. And so if you think back to statistical mechanics, the way you get thermal equilibrium to carry charge is you add a chemical potential. And so what Cohen and Kaplan did was they said, well, what if there exists an explicit chemical potential in our Hamiltonian? We've deformed it by mu times q. And then this would mean that thermal equilibrium would carry B minus L charge. Now, you still have to go from a state, well, yeah, so normally what happens when you put in a chemical potential is that you have your bath here, and it obtains some charge, let's say electric charge Q, but the outside, the thermal bath that's surrounding your system of interest, has obtained a charge minus Q. Now, since our universe has no external bath from which to draw charge, you basically, to reach thermal equilibrium, you need explicit B minus L violation. And so their idea was simply said, put in explicit B minus L violation and a chemical potential, and then this would mean that in thermal equilibrium we have B minus L charge. So what is the unifying theme for everything? Basically, it's new physics. The general reason for this is that...
Sorry, can I just ask you, because I thought that it was actually something different. I thought that what they really had is that they were using the expansion of the universe itself, which gives you a tiny bit of equilibrium, but then with certain operators, it can effectively look like a charge. So is that not correct? Or would you say that's a different way of saying it, or is that not?
So it's partly related. So one of the things that you could do for them is, I guess I had sort of just said, put in an explicit chemical potential. But since we obviously don't want to break, so chemical potential breaks CPT, and so we obviously don't want to explicitly put in a term that breaks CPT into Lagrangian. And so what they wanted to do is say, well, you can break CPT by using expansion of the universe, which breaks T, in combination with the CP violating coupling to dynamically generate it. And so they got a explicit chemical potential, which was proportional to Hubble.
Exactly. So
the expansion of the universe, yeah. And so that's sort of the connection between those two. Yeah. Okay, so sort of the reason why everyone has needed new physics is because they needed to generate some B minus L asymmetry. And since B minus L is a good accidental symmetry of the standard model, it needs to be broken somehow. So this is actually not entirely true because we actually already know a operator which breaks B minus L. In particular, we know that basic gravity does not respect global symmetries. So the argument for this is, imagine you had a bunch of neutrinos and you created a black hole out of them. From classical GER, we know that black holes do not carry charges other than the electric charge or the spin. So in particular, these black holes forget that they were made out of a lot of lepton number. And so when these black holes, as is well known, they decay thermally through Hawking radiation, and the Hawking radiation carries no charge or no lepton number, and so these black holes eventually evaporate down to nothing and lose all the lepton number that was used to create them. So black holes basically can be used to destroy global symmetries. So this is interesting because this means if you gave me a black hole, I could do baryogenesis. What I would do is I'd take a lot of antibaryons, throw them into the black hole would destroy the baryon number for me, and then I will have implemented by hand baryogenesis. So the whole point of this, though, is the statement that in the standard model plus black holes, or standard model plus dynamical gravity, there are all the ingredients needed for baryogenesis. So why don't we just use... So I guess I described to you the argument just now that black holes destroy global symmetries, but so now let's turn that around on its head to make black holes generate global symmetries. So let's look at a perturbative, very non-gravitational toy model, which will be very illuminating. So let's consider the case of right-handed neutrinos with the neutrino masses being generated by the seesaw. So what happens here is that the right-handed neutrino mass breaks lepton number, but if you look at the decay modes of the right-handed neutrino, it decays pretty much symmetrically. And so in some sense you can view this as sort of a situation just like black holes, where you have an object which breaks global symmetries but decays completely symmetrically. And so let's try to study how we can make this asymmetric. So we basically have the two decay modes of the right-handed neutrino. It can go into W plus and a lepton or W minus and an anti-lepton. And so, as is familiar from any QFT book, you can calculate the decay rate of these two guys, and it's proportional to the matrix element squared and integrate over phase space. So the common way people talk about is to make the matrix elements differ for these two objects. And in particular, if you introduce C and CP violating couplings, then tree-level diagrams will interfere with loop-level diagrams, and you'll get an asymmetry. And that the matrix elements themselves will be different for these two guys. But since we have black holes, there are no explicit black hole couplings to objects. So this is not an approach that will work for black holes, which basically leaves us with only one thing, which is to change the kinematics between these two. So in particular, I'm going to use conservation of energy to take this symmetric decay and make it a 100% asymmetric. So the way I'm going to do this is, well, as you can think, I have to change the kinematics between particles and their antiparticles. So I'm going to have to use a chemical potential. So consider deforming your Hamiltonian by an amount mu times lepton number. So now let's look at conservation of energy for these two guys. So the standard conservation of energy is the mass of the right-handed neutrino equals the energy of the W boson plus the lepton, and then plus or minus mu, depending on if you have the final state has plus lepton number or minus lepton number. And notice, since mu is a free parameter, let's dial this larger than the mass of the right-handed neutrinos. Now you notice that energy conservation completely forbids this process here, because obviously energies are positive, and so if mu is larger than the mass of the right-handed neutrinos, this is kinematically non-assessable. And so we've taken a decay that's completely symmetric and made it 100% asymmetric by adding a chemical potential. And so in some sense, this is sort of the simplest way to make a symmetric decay asymmetric. So now let's look at black holes. In particular, we can run the exact same argument. A black hole can decay into a smaller black hole plus a neutrino, or it can decay into a smaller black hole plus an antineutrino. Again, let's add a chemical potential. If the chemical potential is, let's say you go to the rather unphysical regime that it's much larger than the mass of the black hole, then one of these two decays will be completely kinematically forbidden. So, yeah, okay. So, how do black holes decay in the presence of a chemical potential? Well, black holes normally decay thermally, right? This is why black holes destroy global symmetries, right? If you threw something into a black hole, it decays thermally. Thermal equilibrium carries no charge, and so it radiates away, or it destroys their global symmetry. But now, in the presence of chemical charge, a chemical potential, a thermal system carries charge, and so when the black holes are decaying thermally, they are radiating away charge. So basically, what was destroying the global symmetries before the thermal nature is now actually generating the global symmetry. So the basic idea is as follows: well, B minus L is broken by quantum gravity, and so we don't need new physics to explain the baryogenesis. We use the fact that thermal systems can have a non-zero B minus L charge in the presence of a chemical potential. And so we use the evaporation of black holes in the early universe to generate baryon number.
Sorry, how do you decide what's the chemical potential?
Yeah, so I made two assumptions, which was I just said there's an explicit chemical potential. And so now I'm going to describe how you get a chemical potential. And I also assumed that the Hawking radiation was still thermal in the presence of a chemical potential. And I also need to justify that. So yeah, in this next section, I'm going to justify those two statements. Basically talk about the source of the chemical potential and how we get why the black hole radiation is still thermal. Okay, so I'm an effective field theorist. So the way we know that the standard model should be augmented by by both the inflaton and gravity. And so in particular, we should write down all higher dimensional operators that can couple either the inflaton or dynamical gravity to the standard model. So let's consider adding the inflaton to the standard model. So normally the inflaton potential has to be very, very flat in order for it to support inflation. This is usually accomplished by a shift symmetry, which means if you want to couple the inflaton to the standard model, it has to be derivatively. And so then literally the very first coupling you can write connecting the standard model, the inflaton to the standard model, is the derivative of the inflaton coupled to some current suppressed by some operator, by some scale of inflation or whatever. So during inflation, what does this operator look like? Well, you'll notice that during inflation, phi dot is non-zero, which means that there's some operator here that's phi dot over m coupled to J0. Now, what is J0? It's just charge density. So this is literally deforming the Hamiltonian by something that's just mu times q. And so literally the leading operator coupling the standard model to the inflaton is a chemical potential, at least during inflation. And okay, so now what about dynamical gravity? We have to do the same thing, write down all higher dimensional operators coupling dynamical gravity to the standard model. One of them is going to be this guy here, which is del mu Ricci scalar times J mu. The expansion of the universe implies that r dot is non-zero. In particular, r dot turns out to be proportional to h cubed, and so we have an effective chemical potential here, basically due to the expansion of the universe, which is h cubed over m Planck squared. So, yeah. Okay, so a very brief lightning review of chemical potentials. So a chemical potential couples as basically mu times J0, which means you can imagine gauging the symmetry and giving A0 a non-zero value. And so let's consider a free field, free scalar here in the presence of a chemical potential. Like I said, this is effectively like giving A0 a VEV. And then, so if you do the standard decomposition of this scalar into creation and annihilation operators, you discover that it's basically the old one times e to the I mu t. So this means the energy of particles has been increased by amount mu, but the energy of antiparticles here has been decreased by amount mu. So this is just the statement I made before that chemical potentials shift the relative energy levels of particles versus antiparticles. Okay, so this is basically where I'm getting chemical potentials. Now let's try to talk about Hawking radiation, and in particular how Hawking radiation behaves in the presence of a chemical potential. So what is the standard derivation, the easiest derivation of Hawking radiation? Well, the easiest derivation is via the Gibbons-Hawking approach, which is what you do is you take your space-time geometry, you analytically continue it into Euclidean space, and require that there are no deficit angles. The deficit angles are basically if your angular parameter theta doesn't go from 0 to 2 pi. And when you do this, you discover that time is forced to be periodic. And as is familiar from thermal field theory, periodic time is a temperature. And so you discover that the period of time in Euclidean space is the inverse Hawking temperature. And so this means that the black holes are thermal objects. They radiate thermally with a Hawking temperature. But notice that in this derivation, I made absolutely no reference to the matter content of the theory and if there is or is not chemical potentials. And so this gives you the correct temperature regardless of those two. Yeah?
I'm confused by this, though, because you have implicitly made a reference to the matter content, because the black hole solution that has this periodicity in imaginary time is a vacuum solution.
Yeah.
So if you're taking your action and adding a derivative of the scalar curvature to it, you at least have to check that the Schwarzschild and Kerr black holes are still solutions with your new coupling.
Yeah. So in that case, you can say, just let's say you explicitly added a chemical potential. You just deformed their theory by just mu times that, mu times J0. And then that has no reference to gravity, and that in particular will have nothing.
Well, there's a square root of minus G
Yeah.
in there, so that is still going to couple.
Yeah, but you're looking at the vacuum solution, and since the vacuum has no J0, that has no, that gives 0 for the vacuum solution. And so it doesn't change anything
For the vacuum solution.
for the vacuum solution.
But it's not clear that that's what you're talking about when you're talking about adding the chemical potential.
Yeah.
Because
And so, in some sense, though, we're also, since basically by definition, to get a chemical potential, I need some time variation, whether it's, namely the expansion of the universe. So, in some sense, we're also not looking at vacuum solutions. We're looking at dynamical black holes.
Right.
So, like black holes in an FRW expanding universe, or during inflation, or something. And so, it's also slightly different than, they don't need to be exact solutions to the vacuum solution, because the vacuum solution in some sense is boring since it has no time dependence and its effect would vanish.
Okay, but so then you have to make sure that that difference that you're introducing, even if it's very small, the effect you're getting from this chemical potential is presumably also
Very small, yeah.
So you have to at least go back and check and make sure that the first small change isn't wrecking your second small change.
Yeah, you can do that and actually do sort of an epsilon expansion to see that you're not messing up your previous solution, and that does work.
Okay.
So actually, the asymmetric Hawking radiation should actually be familiar to people. In particular, charged black holes emit asymmetrically, right? They have to radiate away their charge. And so now let's repeat this exact same argument in the case of a charged black hole. So for a charged black hole, again, we have an exact solution. We analytically continue it into Euclidean space to find the Hawking temperature. And then you say, okay, this charged black hole must be evaporating thermally. And then you say, okay, it's evaporating thermally, but then you look at the horizon of the black hole, and you discover that because it's charged, the A0 is non-zero, right? A0 is the electric potential. And so there's an effective chemical potential for the electrons at the horizon of the black hole, which is basically the product of the charges over the radius of the black hole. And so, like I said, this derivation could care less about the chemical potentials or matter content. And so you say that this charged black hole evaporates thermally with the Hawking temperature with this particular chemical potential. And in fact, this is what Hawking showed in his original calculation. He actually showed that charged black holes evaporate thermally with the Hawking temperature and a chemical potential that's equal to this. And so the only difference between what I'm looking at now and charged black holes is the fact that I'm putting in an explicit chemical potential. So namely, normally the way for charged black holes that you get this chemical potential is by putting in an electric field, and this back reacts on the geometry. But now I'm just putting in an explicit chemical potential, so there's no back reaction on the geometry. So when you do this, you get a slightly different Hawking temperature. Namely, you get the normal Hawking temperature, and you just have an explicit chemical potential. Okay, so now let's calculate how asymmetric is the radiation. As is sort of familiar, you can take the number density of particles minus the number density of antiparticles, and because one has plus mu, the other has minus mu, you do this as integrals, and you get a term that's proportional to mu cubed. This is the Fermi surface. Basically, right, you fill up fermions until you have mu equals kf. And then you have a second term, which is basically the fact that you put this at non-zero temperature. The chemical potentials I'm looking at will all be extremely, extremely small. And so you can well approximate this by mu times temperature of the black hole squared. And once we're armed with this, we can calculate how much charge is radiated by the black hole per unit time. And so the way you do that is you sum over both GI here, which is the number of internal degrees of freedom of the particles it's emitting, you weight by the charge. You take 4 pi r squared. You multiply by this asymmetry between the two. And a factor of 1/4 comes about because, well, 1/2 is because you're emitting particles outwards rather than inwards, and the other half comes from angular distribution, or angular average. And you can actually you can double check this formula by saying that if we change this difference to a sum, we should be reproducing the Stefan-Boltzmann law. And anyways, so finally you find that the charge, the B minus L charge emitted per unit time by a black hole is proportional to basically just the chemical potential. So, yeah.
It's just a technical matter, but if you want to do this and get a number that you actually believe, black holes aren't black bodies, they're gray bodies, and the gray body factors can give you differences of up to 60–70%.
Yeah, so here we want order of magnitude,
Okay,
correct?
that's fine.
And so,
That's fine.
yeah. And so the gray body factors you basically take into account by the fact that these guys start scattering and interacting as you. So right at the horizon, it's a perfect black hole, but then so you get away the gray body factors. So yeah. I mean.
Okay.
You
wrote that so precisely. I wanted to make sure that it
Sorry.
was,
Yeah. So basically, when doing baryogenesis, you're happy to get order of magnitude the correct answer.
Okay.
And so that's, I'm making some approximation to just see, can I even get order of the magnitude correct?
Yeah. Okay.
Yeah. Okay. So you get the somewhat surprising result here that the charge being radiated, or the B minus L charge being radiated per unit time for a black hole is independent of its size and is proportional just to the chemical potential. Of course, if you included this mu cube term, then you get some more complicated dependence. So finally, we can just say, what's the total asymmetry emitted by a black hole over the course of its lifetime? Well, you just take this number and multiply by the lifetime of the black hole. A very standard calculation is you can calculate the mass of the black hole as a function of time, and then you just take the lifetime and multiply by dq dt to get the total charge. Okay. So now I'm going to take the evaporation of black holes in the early universe in an attempt to do baryogenesis. So first statement is, how do you get black holes in the early universe? Most people, and for the purpose of my story, you can just say, we assume that there are some primordial black holes floating about. There are not very many standard stories for them. So basically, I showed two possible sources of the chemical potential, either the derivative of the Ricci scalar or the derivative of the Inflaton. And so during inflation, it's basically impossible, well, not impossible, but it's very difficult to generate pretty much anything. And so I'm not going to look at inflation, really. After an inflation, there are several standard stories for how to produce black holes. Sort of the easiest way to get small black holes that evaporate is from hybrid inflation. And so what happens in hybrid inflation is that you have a slowly rolling field, and then at some point in time, very abruptly, a waterfall field sucks all the energy out of the inflaton. And so this transition is very sharp, and you can calculate it and show that it generates large density perturbations. And so after reheating, when these density perturbations come back into your horizon, what's a large density perturbation? Well, it's taking a lot of stuff and crunching it into a very small space. And so that turns everything into black holes. And so what happens in a large region of parameter space for hybrid inflation is that your whole universe gets crunched into many different black holes. And then eventually you have to wait a long time, these black holes evaporate and reheat your universe, and then you proceed from there. So I'm going to basically be using that particular approach, since that's sort of the only case I know of which has a standard story. Okay. So if we're looking at black holes after inflation, the dominant term for the chemical potential comes from this del mu Ricci scalar over m Planck squared. And so again, as I mentioned before, this gives h cubed over m Planck squared. But in particular, you notice that this operator has a 1 plus w, meaning it vanishes during de Sitter expansion, and it has a 1 minus 3w, and so it vanishes during radiation domination. So the statement of 1 minus 3W being equal to 0 during radiation domination is not entirely true. In particular, the trace anomaly will set 1 minus 3W equal to non-zero. The way you can see this is that the stress energy tensor is basically, right, energy density, pressure, pressure, pressure. When you trace it, it gives 1 minus 3W. But because trace of T mu nu is proportional to beta functions, right, the scale anomaly, so this is not quite 0 during radiation domination. A bunch of people calculated this for us, and what you find is that for an arbitrary gauge theory with NF flavors, you find this rather complicated result. What's relevant for the standard model is that when you put in standard model values for everything, this is basically a part per thousand. Okay. So the approach I'm taking is using the hybrid inflation theory, where at some point in the universe, black holes dominate your entire energy density of your universe, and reheating comes about eventually when the black holes evaporate. So if we assume that at some point in time, we have some number density of black holes here, which is based number density equals, I basically weighted it by the volume of the black hole.
Sorry, but maybe sorry, can you just go back? Because maybe,
Yeah.
I'm not sure if it's important, but is there, go back one more. I mean, is there, well, one more. I'm just wondering, why does the chemical, is there a way to understand why the chemical potential vanishes in the limit where you have a traceless stress tensor?
That's just, not that so I don't know of an easy, simple answer to that. I think it's basically just the peculiarity of looking at the time derivative of the Ricci scalar.
Well, the Ricci scalar is equal to the trace of the stress energy.
Okay, yeah.
By the field equation, so if the
Right,
trace is
actually,
zero,
yeah.
then
No,
that
it's
term
not in
just
four
goes away.
dimensions. Not in four, this is 4 dimensions.
Yeah,
The trace is the square of some,
no, R is,
trace is
the
dimension
Einstein
4.
field equations say that R is equal to some constant times T.
Oh, I see. Okay, yeah, that makes sense.
Yeah.
Yeah, you're right. I see. Okay.
Okay, so yeah, let's assume we have some number density of black holes. In this case, I weighted it by the radius of the black hole. So basically, epsilon equals 1 means our entire universe is chock full of black holes, and obviously epsilon is going to be much smaller than 1. So what happens is basically the universe continues to expand until the Hubble is equal to the decay constant of the black hole. And once this happens, the black holes all decay. And from this, you can basically calculate what the number density of the black hole is. You can just calculate epsilon in terms of the mass of the black holes. And so once you do this, you say all the black holes all evaporate. You basically set the energy density of the black holes equal to basically T to the 4th. And so you can solve for the reheating temperature. And again, you can calculate the entropy density, which is T to the cubed, basically. Okay, so now that we have the entropy density, we want to find the number density of B minus L divided by the entropy, because that's what we measure today. And so to do that, we need to find out how asymmetric are these evaporations. And so now we have to think about the chemical potential a little more carefully. So there are basically 2 contributions to the chemical potential here. The first contribution is the fact that we're in a matter-dominated universe. So we can calculate, basically before, we can just set W equals 0 here. But as I sort of is clear from the case of the charged black holes, which actually is important, is the chemical potential at the horizon itself, not the coarse-grained chemical potential. And so what we would have to do is look at a universe, which is an FRW expanding universe when coarse-grained, and then put in lots and lots of black holes and calculate what is del mu r at the horizon. This is not anything anyone has done, and it's too complicated for me. But the closest example I've been able to find in the literature is called the Mcviti solution. And so this is the assumption that you put a black hole in an expanding FRW expanding universe and impose that it has constant mass. Unfortunately, this solution actually has no physical consequence, basically because in order for the black hole to have constant mass, there needs to be a negative pressure existing at its horizon that pushes away all matter. And so we actually have, these obviously don't describe physical black holes, and so we don't know what del mu r is at the horizon. The second source of del mu r is the fact that at the horizon of the black hole you have Hawking radiation. And so Hawking radiation means that you have, you have h squared goes as rho over m Planck squared, and rho is t cubed, or sorry, t to the fourth. And so you have the fact that classically del mu r is 0 at the horizon of, let's say, a black hole in Minkowski space. But then once you include the first order quantum corrections, you have it evaporating and radiating off Hawking radiation. And these guys means del mu r, which is proportional to h cubed and proportional to energy density at the horizon, is non-zero. And so we're going to use this guy here, basically because I don't know how to calculate the other contribution to the chemical potential. So, okay, I'm going to basically go over this very briefly because it's a rather boring calculation. So you basically know the chemical potential in terms of H. We know H in terms of the temperature of the black hole, and we know how much charge is being radiated per unit time per black hole. And so you can find the total asymmetry by taking the number density of the black holes multiplied by the total number of total asymmetry generated per black hole. And since we know things like the temperature of the black hole, the mass of the black hole is a function of time, we can do this integral. And so the end result that you get is basically the abundance here, which is the number of B minus L charge divided by the entropy, is equal to 10 to the minus 8 times, basically, here you go, m Planck to the 5 halves over mass of the black hole to the 5 halves. And so experimentally, we have measured the B minus L, y B minus L here is 10 to the minus 10. So what you'll notice here that in order for this guy to give you 10 to the minus 10, you either need large couplings. Okay, so just to remind everyone, the way I defined lambda here was from this coupling here, some lambda times del mu r over m Planck squared. So large lambda means this operator is not suppressed by the Planck scale anymore. So you either have a large coupling here, lambda, or you have basically Planck scale mass black holes, which you don't trust your calculation anymore because, yeah. So you either need large coupling or live in an incalculable regime.
What is y again? I thought you said it was less than 10 to the minus 10.
Yeah, so observationally, it's equal to 10 to the minus 10.
So you could have lambda is 1 and black hole.
Yeah, a few m Planck.
Yeah.
Oh, I'm sorry. It's the other way. It's down.
Yeah, sorry. It's on the bottom here.
Okay.
Yeah. And so, yeah. So the hope was to, in the standard model, do a baryogenesis mechanism that has no new physics. And the end result is basically large couplings or Planck scale black holes. And if you wanted to actually get reasonable values, you can put in, for example, here, instead of being suppressed by the Planck scale, if you suppress it by the gut scale, then that's lambda here equals 10 to the 10. And so you can have very reasonably sized black holes and generate the correct asymmetry.
So this is just to be clear. So your problem is you're getting too much asymmetry.
Too small of an asymmetry. And so to get a much larger asymmetry, I either need a much larger chemical potential, which is basically cranking up this operator here, or we need much smaller black holes.
Right, sorry.
Yeah. Yeah, the problem is basically here this
Keep
annoying 10 to the minus 8 number.
Yeah, I keep forgetting the large black hole mass is the infrared. That's my problem.
Yeah.
Okay,
Yeah.
thanks. Yes.
And so, I mean, in some sense, it's not that bad if this is suppressed by the gut scale. but that means there's new particles at the gut scale, and sort of the way I had tried to sell this was I was hoping to try to get no new physics up to the Planck scale. But, okay, there could be new physics, and that's just suppressed by the Planck scale, or sorry, the gut scale. The other option is to try to do things in inflation. So during inflation, mu here is proportional to just 1 power of Hubble, and not Hubble cubed over n Planck squared. And so this is actually something like 10 orders of magnitude larger. And so if there were black holes around during inflation, their decays would be very asymmetric, and you could get baryogenesis very easily. But the problem is it's very difficult to produce black holes during inflation. It's difficult enough in warm inflation models to really get non-zero particle numbers.
What about during reheating? I mean, somehow during reheating you may have an oscillating scalar field.
Yeah.
And so you might have this operator enhanced,
Yep.
but you're in a matter-dominated background. Or it's more,
Yeah.
a little more complicated than that, but roughly it's
Mm-hmm.
you're in a matter-dominated background.
Yeah, and so that would work if you found a good way to get, so basically sort of tried to combine these two approaches and say large density perturbations give you black holes while you're reheating, or while you're
Well, I think the issue there is going to be that, I mean, you're literally, in the
You need an
simplest
overdamped.
approximation,
Yeah,
you're just oscillating.
yeah,
And so then you go one way,
Right.
you'll generate it, and you'll wipe it out going
Yeah.
the other way.
and so it needs
But
to be basically
that-
overdamped, so it
Yeah,
only
but you've got
goes
10
one way.
orders of magnitude, so then there's going to be
Yeah.
some damping, and it'll be,
Yeah,
it seems like you could still win.
and so yeah, so there is probably a way to make you win. You just have to sort of live in some small corner of parameter space, where things just happen to be happening or occurring at the right time.
Has
this
anybody ever looked at production of black holes during reheating? If you just have some
Not that I
standard
know of.
decoupling reheating scenario?
I mean, not that I know of. I think people just haven't had a reason to.
Well, people wanted to make black holes into dark matter, so.
That's right.
Yeah,
But
but those are
people
also
thought
much
about-
larger black holes, because the black holes I'm interested in are ones that have evaporated before BDN and whatnot. And so, yeah, the ones they are trying to do are sort of generally gravitationally, created gravitationally, and so they're much, much larger, and so haven't decayed by now. But yeah, there should be some way to make it work. It just it's slightly more involved than what I've said so far.
And just to be clear, the previous thing you are, when you put your numerical estimate, you put in some standard model-like suppression for the trace of the stress tension.
Yeah.
That's included.
Yeah, and
that
so
was, that was some 3 orders of magnitude.
magnitude, yeah. And so if you had, let's say, gut theory, there was a lot more beta functions. It's a lot larger, and you could actually get 1 minus 3W to be like of an order a 10th or whatnot. Even order 1 if you have these sort of models which have a ton of matter, and so then you have to worry about Landau flows. Yeah. So yeah, there are a lot of different ways to sort of tweak at this once you go beyond just standard model to get it to work. Okay, so finally I'm going to sort of shift gears and talk about some work in progress that is not exactly the same thing, but not 100% unrelated. And so basically what I've been talking about before is basically that thermal equilibrium carries charge in the presence of a chemical potential, and basically sort of cool things you can do with a chemical potential. And so why not use sphalerons to do this? In particular, sphalerons break B plus L, and so if you have sphalerons in the presence of the chemical potential, rather than relaxing you to the sort of the B plus L equals 0 state like they normally do, they would relax you to a state which has non-zero B plus L. So if there is a chemical potential, let's say for B plus L, that is non-zero when the electroweak sphalerons freeze out, then you will have the sphalerons themselves will be doing baryogenesis for you. And so this is sort of an amusing way of doing electroweak baryogenesis. Numerically, you can calculate this numerically, and you find that you need a chemical potential that's basically 10 to the 3 or so eV during when sphalerons freeze out. And so that's something that's actually much larger than Hubble. So we actually need a very large chemical potential to make this work. So what's the first source of a chemical potential? Well, the first thing anyone guesses when they hear this are axions, right? Because axions naturally couple to the B plus L current. And so if an axion was slowly rolling when sphalerons freeze out, then the axion will, well, then because you have a chemical potential, the sphalerons are decaying asymmetrically and would give you baryogenesis. It turns out numerically that this doesn't quite work, basically because you discover that the axion would have to roll distances much larger than Fa, so it either need a monodromy, it'd have to be non-compact or something. And so let's look at a slightly different way of generating the chemical potential. So in particular, let's use dark matter. So if you have the coupling J mu dark, J mu B plus L, then if dark matter is asymmetric, that would mean J0 dark is non-zero. And so you literally have dark matter sourcing your chemical potential. And so this is sort of an amusing thing, right? Because what you're doing is you are not transferring an asymmetry from one sector to another. Notice that this scattering causes dark plus anti-dark goes into baryon plus anti-baryon. That doesn't transfer any dark asymmetry. This operator doesn't break any U1 dark. So this is not transferring an asymmetry from one sector to another, but using an asymmetry in one sector to generate an asymmetry in another. So sort of the microscopics of this chemical potential is the fact that you have some process, it gives you baryons and antibaryons. The baryons have the ability to scatter off of the dark matter particles, but the antibaryons can't scatter off of anti-dark particles because there are none of them around. So that's sort of the microscopic way of generating this asymmetry. And so this is also extremely predictive because the chemical potential is just the number density of dark matter over some UV cutoff squared. And we know what the energy density of dark matter is today. And so there's literally only one free parameter in this theory, which is basically lambda squared times mass of the dark matter, right? Because as soon as you turn this number density into an energy density by dividing by mass of the dark matter. And so since you know what the baryon number abundance today is, you can calculate what the UV cutoff here has to be in terms of the mass of the dark matter. And so what you see here is that it's actually, rather, if you put the dark matter mass at sort of GeV scale, this is an extremely low cutoff here. And so this should be testable by a lot of different ways. So sort of one way to test this is just sort of at the LHC, because the operator I'm interested in, here you go, is this guy here. And so this goes baryon, proton, antiproton goes into dark matter. And so you get monojet bounds on this II. This means that the cutoff has to be larger than about a TeV. This is also direct detection, right? Because it describes dark matter particles scattering off of baryons, protons. And so what it turns out is actually, since if you look back here, that this is of the GeV scale. Once you make the dark matter lighter than a few GeV, then it doesn't leave enough recoil energy. And so it's actually not constrained by direct detection very well. The strongest bounds actually come about from the fact that whatever UV completion generates this operator will also generate operators like this. And this is extremely easy to probe at the LHC because this is protons into pairs of leptons.
So is there like a lab monophoton constraint?
Yeah.
The energy is lower than the cutoff scale.
Yeah, so the LHC will bound UV cutoffs like between TeV and like tens of GeV, and then you have to start going to different experiments to go to different lower cutoff.
But then I don't understand. I mean, so doesn't that already rule out? Doesn't that already rule you out? So even without this? Or?
Yeah. So that basically means that this UV cutoff has to be some large number.
Right.
In particular, that means this guy here, mass of the dark matter, has to be very small.
Which probably also doesn't work.
Yeah, and so there's actually a lower bound on the mass of the dark matter, which is basically KeV due to structure formation.
Right.
And you discover there's actually only a very small region of parameter space where this is valuable. Namely, the dark matter mass has to be between keV and a few hundred keV. And so it's sort of constrained from both directions. Astrophysics means it has to be heavy, which means that the UV cutoff must be small, which makes it sort of detectable at the LHC. So it's sort of an amusing combination of, you can poke at it from different directions, and you find a very small region of parameter space. And it's sort of also amusing because usually when people talk about asymmetric dark matter, they're talking about GeV scale dark matter. And this is an asymmetric dark matter model where the dark matter is required to be keV.
I'm wondering if the bond would be even stronger when you take into account the like neutron star cooling or and the supernova cooling. For this light.
Yeah, so for a keV scale, when we looked at supernova, so yeah, this is work in progress, but when we looked at supernova, the constraints were also around like 6 TeV or something.
Oh.
And so it was somewhat comparable in strength with LHC bounds. Yeah. Okay. So to conclude, sort of the leading order operators connecting the standard model to the gravity or the inflation can act as a chemical potential. And so when you combine this with black holes, you can basically cause black holes to decay asymmetrically. And sort of it's amusing because it sort of provides an alternative to electroweak baryogenesis in the sense that it's a baryogenesis mechanism that basically requires no new particles that we don't know already exist. And so sort of random other statements are sort of, well, I assume basically just a standard model. If you do other things, you can just assume other slowly rolling particles. This can sort of help relieve the problem that the chemical potential is too small. We basically need other sources of time dilation. Like I mentioned before, it'd be interesting to understand the chemical potential at the horizon of these black holes explicitly when you have, for example, a matter-dominated universe of black holes. And it'd be really nice if there's some way to find some observational consequences for this. Because the way I have it set up right now is that Hubble is providing your time dilation. And unfortunately, right now, Hubble is 40 orders of magnitude smaller than it was in the early universe. So this is basically completely and utterly unobservable in the current universe, like currently, but it'd be interesting if there was some way to tweak it and make it actually predict something about current black holes. And finally, just if you play around with chemical potentials during the electroweak phase transition, you can sort of make scalarons do electroweak baryogenesis for you. And I think that's it. Thank you.
Any questions, comments? I have a bunch of things with all this kind
What
of...
happens if you include the cosmological constants? Do you have any effects with that?
So the cosmological constant, including that, doesn't really seem to change much because what we need here is some source of time violation. And so the CC by itself doesn't do anything for you. If you're, I guess, in the region of time when the CC dominates the expansion of the universe, that gives you a very large Hubble that you could use. But sort of by itself, it doesn't quite give you anything that useful.
And one more comment, at some point you said that for some of the solutions, you have repulsion for all the matter.
Mm-hmm.
I know for Reisner and Nordstrom solutions, we charge black holes.
Yeah.
This is true for opposite charge, but then actually the opposite charge at some point can go through and annihilate the black hole.
Mm-hmm.
So I don't know what do you mean exactly for all matter. And you can have opposite charge that can overcome this repulsion.
So your statement is that, sorry, could you repeat that? I don't quite get what.
You said that there is a repulsion region around the black hole, especially if it's charged. And for Reisner notion, it's true.
So this is the gray body factor, or?
This is coming from looking at the geodesics. And basically you find that for geodesics, unless they have enough charge, they will not be able, but this is on classical level, I don't know how it works on the quantum level. It will not be able to penetrate when it will be kind of turn around. It will stop and turn around. And it will happen even for chargeless, particle with no charge.
Yes.
But then the opposite charge particles, they will eventually go through.
Yeah, so I guess that is the statement of that there are very non-trivial gray body factors so once the particles get emitted by the horizon, they could sort of get stuck and turn around and go back to the black hole. And so I guess sort of my approach has just been, for baryogenesis, this is an extremely small number, so the goal is just to try to get it to order of magnitude correct. This is going to give you order 1, like half of the particles may turn around or something like that. But it won't change the answer by orders of magnitude.
Okay.
And so the goal is just to try to see, does it work just order of magnitude level? Yeah. And so that's definitely an important thing that you have to think about if you want to get the number exactly correct.
Okay, so if there's no more question, let's thank the speaker again.